Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time, intelligent and autonomous algorithms. Present the conference. Energy efficiency, innovation and digital transformation in the heavy industrial sector. An approach based on scientific praxis. Edited by Jesus Velasquez Bermudez, Chief Scientific Officer of HI. Dictated in Cartagena de Indias, on February 22, 2023. In 1987, the World Commission on Environment and Development defined the problem of sustainable development, envisioning the future in which we live, in the text. Our common future. Humanity must have the ability to make development sustainable, to ensure that it meets the needs of the present, without compromising the ability of future generations to meet their own needs. The concept of sustainable development does imply limits, not absolute limits, but limitations imposed by the present state of technology and social organization on environmental resources, and by the ability of the biosphere to absorb the effects of human activities. But technology and social organization can be both managed and improved, to make way for a new era of economic growth. The Commission believes that widespread poverty is no longer inevitable. Poverty is not only an evil, but sustainable development requires meeting the basic needs of all and extending to all the opportunity to fulfill their aspirations for a better life. A world, in which poverty is endemic, will always be prone to ecological and other catastrophes. As a result, industrialized countries have begun to reduce energy consumption per economic unit of gross domestic product produced. Artificial intelligence transforms business sustainability. The use of decision-making artificial intelligence, DMAI, is becoming more common, to help companies achieve their carbon emission reduction goals, and become more aware of the impact their business operations have on the environment. According to a study conducted jointly by Microsoft and PwC, the use of artificial intelligence can help companies provide valuable information, and help them make more informed decisions, leading to better results in their sustainable practices, and in their economic results. In this sense, the research reveals that DMAI can improve energy efficiency, by analyzing data from sensors, and other sources, to identify areas where energy consumption can be reduced, optimizing mathematically their operations, and reducing polluting waste. The DMAI is an essential factor for sustainability. It's the key to unlocking knowledge, driving industrial efficiency, and enabling the transformative change we need to address global environmental challenges. HI is an expert company in decision-making artificial intelligence, with extensive scientific knowledge in the modeling of energy systems and complex industrial processes, two areas necessary to face industrial energy efficiency processes, which, although the fundamentals that justify it are known, realistic mathematical models are required that allow accurate calculations to be made, to know the real impacts of the decisions that are made. Given its scientific knowledge and its social awareness, HI offers to the interested companies a diagnosis, free of charge, of a general analysis of the mathematical modeling solution and the technological infrastructure that it considers part of the solution. The conference presents a good variety of use cases in different types of companies. Artificial brains, artificial intelligence, and mathematical programming integration. It is the main area of research and development plus innovation of HI. Artificial brains correspond to the scientific foundations, more specifically to the mathematical foundations, which allow multiple mathematical models, algorithms or robots, to be connected, exchanging information between them to obtain a common goal, and acting as holistic intelligence of organizations, or parts of them. Like the human brain, the artificial brain is made up of the following artificial components. Neocortex acts as an organizer of the connectivity of mathematical artificial neurons. Hypothalamus, it is the central processor that coordinates all the models included in an artificial brain, and hippocampus, it is the memory of the brain that stores the history of what is happening in terms of mathematical model runs. It is coordinated by a traditional artificial net. Smart grids and demand response is the fundamental knowledge required by an industrial company to access the new commercial world, which holds the future for electricity consumers, and energy in general. Optimizing the planning and operation of new electricity grids is the prerequisite for increasing so-called industrial energy efficiency. Achieving industrial efficiency is a highly complex technical process, due to the multiple aspects that must be handled. The electrical system of the future implies a totally different conceptualization of the supply of electricity. The current system, which is gradually becoming obsolete, operates based on a hierarchical structure. In this system, as voltage levels are lowered, the generators approaches consumers, industrial and residential, who only consume energy, at a price that depends on the generation system. In these systems, consumers are price takers agents. Smart grids are based on a multi-level meshing system, in which users, industrial and residential, become potential small and medium-scale generators, who can manage their demand, affecting the price at which they buy or sell electricity. In a regulated environment, generation, transmission and distribution are operated by a vertically integrated company, usually a state-owned enterprise that has a monopoly on the supply of electricity. On the other hand, in a deregulated environment, different parts of the electricity grid are owned by different companies, most of them private, and the electricity markets provide a platform that fosters competition and active consumers. Due to the new power technologies, this liberation of the electricity market has reached the industrial factories that must face this new opportunity. To achieve energy efficiency, industries must include energy management and carbon footprint control in their digital transformation processes. This involves two major processes related to advanced analytics. Offline optimization, planning. This stage is related to the optimization processes that must be carried out prior to the commissioning of the energy system, redesigned in accordance with modern advanced analytics methodologies, and the computational power available. Part of this stage are the following activities. Redesign the energy supply system, in accordance with the new power technologies in force, and with a vision of the near future, due to the speed of change of these technologies. Presumably when the industrial plant was built, new concepts, such as smart grids, did not exist. Optimize the industrial process using complex modern mathematical models, since it is possible that the industrial plant is operating based on outdated mathematical models, which do not consider the computing power of current methodologies, for example, advanced, parallel and distributed analytics, and integrating the planning and programming of industrial processes, transformation of matter, with industrial services, transformation of energy. This is a core element in the whole process. The diagram shows what an old power supply system might look like. A modern energy supply system is impacted by new power technologies, and by advanced analytics, artificial intelligence, machine learning, and large-scale mathematical programming. The second major process of digital transformation is related to online optimization, scheduling. The final part of the process of restructuring an energy system is called demand response, which involves the participation of consumers in energy systems, as a way to optimize their benefits. At this stage, the consumer should use an optimization model for the planning and scheduling of dispatches of the energy system, together with the optimization of production, and use models aimed at optimal real-time control of energy system dispatch, and energy trading and risk management, ETRM. Demand response is the name given to the actions that consumers, industrial and residential, can, or should, take to act properly in the new electricity system, which includes actively participating in the marketing. The electrical system can be conceived as made up of three types of agents. The generation, which includes the traditional one, based on large generation plants, and renewable, originating in new renewable energy sources, such as wind, solar, tidal, wave, biomass, and others. We must not lose sight of the incursion of hydrogen, green and blue, as a new type of clean energy, which is changing the landscape of the future of electricity generation and storage. Transmission and distribution, as the means of ensuring the balance that must exist between supply and demand. Consumers, classified as residential, commercials, and electricity-intensive industries. Optimal demand management should produce two results. Demand response, aimed at reducing electricity consumption in industrial plants, and energy efficiency, aimed at reducing the demand for total electricity, and the costs associated with its supply. This entire process includes the control of pollutant emissions. Demand-side response is systematic activities by utilities and government to change the amount, and/or timing, of the customer's use of electricity for the collective benefit of the society, the utility, and the customers. It is the direct consequence of smart grids, which allow demand to stop being a passive actor, which only takes prices, and becomes an actor with the capacity to respond, actively participating in the market. To act as an effective agent, industries must know the structure of the electricity system and market. The diagram presents a typical structure, indicating the relationship of consumers with the physical power grid and with the market. In this structure, two types of agents are displayed: interconnected system operator, ISO, and consumers. ISO, as the name implies, operates the grid, dispatching centralized electrical resources, and it manages markets, creating incentives for demand management. For their part, consumers receive price signals from the market, buy, and/or sell electricity to the market, and consume electricity from the national grid, and/or produces electricity with their smart grid. The consumer demand response must be based on what the regulator establishes, and the market ISO can be classified as dispatchable response. Traditional services are direct load control, generation contributed to the system, ancillary services, such as AGC, automatic control generation, and interruptible load, authorization for ISO to decrease, or interrupt, the consumption of an industry. Non-dispatchable response corresponds to actions to adjust the profile of cargo taken, or dispatched, in response to dynamic changes in prices. The image presents a more extensive diagram of demand management. To participate in demand response, the type of company must be matched with the opportunities provided to companies. In 2007, the North American Electric Reliability Corporation, NERC, published a study in which it analyzes different types of industries, and relates them to the type of services they must offer, considering their industrial processes. However, it should be noted that at that time there was no possibility of considering energy storages, which allow smart grids that can participate in dispatchable demand. It should be noted that, in industrial environments, the possibilities of energy storage can be very different from traditional ones, since there are industrial processes that can store energy as part of the process. Demand response and energy efficiency is a major issue for heavy industry, as it is an opportunity to significantly increase its profits, and to decrease the carbon footprint of its industrial processes. Turning the process of maintaining an eco-sustainable into a good business. To achieve optimal planning and scheduling of energy management, 4 major challenges must be faced. Accurate modeling of process dynamics and operational flexibility. Integration of production management and energy management. Optimization at multiple space-time scales, and optimizing decision-making under conditions of uncertainty. These aspects will be discussed later. Market participation is, in practice, a mandatory requirement if you want to maximize the return on investment in your company's smart grids. This has given rise to the acronym ETRM, Energy Trading and Risk Management. Initially, this function only existed in electricity companies, in open markets. Today it is extended to any company that wishes to participate in the electricity market, and other energy markets. ETRM involves 3 fundamental aspects. First, negotiations and contracts, legal means of buying and selling energy between 2 agents. It can be through buying and selling in the spot market, non-standardized bilateral contracts, financial derivatives such as futures and options trading. This is possible where such markets exist, and transactions in secondary markets, which buy-sell energy, and then go to the main market. Second, financial risk management, a fundamental part of the buying and selling processes in markets with uncertainties. There are multiple risks to control, for example, liquidity, prices, quantities, and default. This must be done by means of mathematical modeling aimed at the scientific management of financial risks. Third, generation and/or demand offers. Normally the market moves in two steps. The day before the dispatch, the participants make bids for an auction, whose allocations will be defined by the ISO. These assignments are mandatory. On the day of dispatch, a redispatch is carried out, in real time, or in the short term, to resolve the contingencies that occur, and thus guarantee the supply-demand balance. This process is done by the ISO using optimization models, which depend on the ISO. The result of the ETRM is the contracts that will be signed. To do this, the company requires appropriate tools that allow it to analyze the decision-making process. Mathematical theory indicates that stochastic optimization models that include hedging financial risks are appropriate. Energy consumption and industrial processes. Most industrial processes are variable speed. Energy consumption as a function of process speed is not linear, it is exponential. The operator must be aware that production facilities do not have a defined capacity. This is set according to the speed of the process, and the time that this speed lasts. That's a decision variable for plant operators. The graph presents the curves of fuel consumption versus ship speed. There are 5 curves, for different revolutions per minute, which are related to different blade pitches. Exponential nonlinearity is evident. The table presents the energy consumption versus speed of the AB103 high-speed train. Column 2 analyzes the kWh consumed per kilometer at the 3 speeds analyzed. The nonlinearity is noticeable. The graph presents the energy consumption versus flow curves in an oil pipeline. 7 curves are presented, for different outlet pressures at the pumping station. Exponential nonlinearity is evident. Production optimization and energy management. The focus is related to the integration of the two systems through integrated mathematical modeling, the production system, and the energy system. As an example, reference will be made to a brewery. Optimization of energy management. The optimal management of the energy of industrial systems implies a holistic position, which integrates the planning of the production of goods, with the energy services that are consumed in that production, and finally integrates it with the possibilities of self-production and negotiation of energy. A supply chain integrates multiple production plants, which must be modeled individually, each with its own peculiarities. High SANDOP, Sales and Operations Planning, is a highly complex aggregate mathematical model for the industrial sector. High SANDOP optimizes industrial production in all facilities that make up the supply chain. The level of aggregation is related to the detail of modeling the processes, in the process units and in the production lines. The goal of optimization is to determine the production plan that will minimize production costs, or that will maximize economic utility, and meet the demand for finished products during the planning period. Hypothalamus AI considers the production process as a union of two processes. Product transformation, conversion of raw materials into commercial products, through process units, and energy transformation, processing of the auxiliary industrial services required by the process units, and which are consumers, or producers, of energy in the service units. To optimize energy efficiency, the first step is to optimize the integrated supply chain, since this is the part of the production process that consumes the most energy resources. The second step, in the optimization of energy efficiency, is the integration of the industrial process plant with the industrial services plant. The optimization of industrial services, high ISO, corresponds to a mathematical model aimed at the optimization of energy consumption and other industrial services in industrial plants that include industrial service plants, such as refineries, petrochemicals, and in general large industrial manufacturing plants. These services often include self-generation, cogeneration, and the exchange of electrical energy with the interconnected electricity transmission system. The aim of the model is to minimize the consumption, or cost, of the energy required by industrial processes. The industrial service system is combined with the production process model, to comprehensively optimize the transformation of raw materials into finished products and energy management. The SANDOP ISO model integrates the SANDOP and ISO models into a single optimization model. It is possible to coordinate the two models through two stages. Optimization of production through the SANDOP model, and Optimization of energy consumption using the ISO model, with SAND-op results as a border condition. The increased volatility of electricity prices, together with new opportunities for demand-side management, and the possibility of meeting energy consumption with various electricity, gas and other energy contracts, should be complemented by optimal operation in energy-intensive industrial processes. There are different sources of electricity supply, which are characterized by connectivity with the different entities of the system, and by the form of contracting that exist for them. Energy of the interconnected system. Power purchase agreements, PPA. BOMT, construction, operation, maintenance and transfer, contracts. Equipment rental contracts. Own generation, and energy generating industrial processes. Once the best option has been decided, the energy exchanges that will take place must be planned and scheduled to coordinate all sources. Flexible industrial processes are ideal for energy management, as they can adjust their topology and technical characteristics to real-time operating conditions. Perhaps one of the best examples of a flexible machine is the high-performance cars of Formula One. The operational flexibility of the electricity system is essential for an optimal response in demand management. Industrial processes, such as those carried out in cement plants, consume large amounts of electrical energy. During operation, these plants can turn on and off an arbitrary number of crushers and mills, and thus adjust the optimal consumption of electrical power, according to the prices of electricity in the spot market. However, the rapid change in energy consumption does not allow them to provide complementary services, such as automatic generation control, or AGC. On the other hand, the clinker furnace has an important rigidity, since its speed and operating conditions must not be permanently changing. Some ancillary services require a continuous change in consumption. On the other hand, certain industrial loads, for example, furnaces, cannot be turned off, or turned on, quickly, and therefore only provide discrete changes in consumption. Ancillary services need a much faster response to the change in power consumption. The possibility of coordination, with regulation and monitoring of the load, with the help of energy storages provides a smooth and continuous changeover. NSIDE considers there are 4 types of industrial processes that are the most common, from the point of view of flexible electricity management. Continuous, on and off, works continuously, and can be turned off, or on, at any time. Continuous modulated, works continuously, and the level of their operation can be adjusted. Batched, on and off, produces batches of products, and can be turned off, or on, at any time, and multi-product process, operating conditions change continuously. Flexible industrial process. Case, industrial gas production at Praxis. The cryogenic energy storage, CES, involves storing energy in the form of liquid gas, which vaporizes as it is conducted to turbines. Including CES in an air separation plant has the following benefits. Increases plant flexibility for changes in electrical load. Storage of energy purchased to sell later the market, during periods of higher prices, and create additional revenue by providing reserve operational electricity capacity. The diagram presents the traditional industrial process, in which the air separator unit, as, is fundamental, because it generates all the types of industrial gases that are processed at Praxis. The traditional system meant that as production was directed to storage tanks for gases in liquid form. To give flexibility to the process, cryogenic gas storage units were created at the AS outlet. In this way, depending on the short-term planning, it is decided in which type of tanks the industrial gases are stored. As a complement to the storage system, the electricity generation system is incorporated, from which it is possible to provide electricity in the primary market, or sell safety reserve for the AGC process, in the form of cryogenic gas stored in the CES inventory. To implement the new system, a mixed linear integer programming, MILP, mathematical model was developed for plant scheduling, and a robust optimization scheme was applied for the management of the AGC reserve. Tests of the model demonstrated its applicability to validate the design of the new facilities, and to analyze their profitability. The image presents the comparative results of the operation of the Praxis plant, with and without cryogenic storage. Energy efficiency mining metallurgical. Case, cement industry. It corresponds to a mathematical model developed by hypothalamus artificial intelligence, to optimize operations in a cement factory, with an emphasis on energy efficiency, material mixing, and emission control. The image presents a semi-detailed diagram of the cement supply chain, considering 3 production alternatives: semi-dry, dry, and wet. The image presents an overview of the cement production process, from lime mines to the production of fine cement. From an energy point of view, the process can be divided into 3 stages. Preparation of the clinker paste includes transporting, crushing and grinding the raw material, and mixing it with correctors, mainly uses electrical energy. Clinker baking, conversion of clinker dough into clinker, is performed in a linear oven, and consumes thermal energy and chemical energy, and grinding of the fine cement, mixing the clinker with additional materials, until the appropriate granularity is achieved. It mainly uses electrical energy. The image shows the energy consumption throughout the process, which is divided into electric power in the milling of raw materials, thermal energy and chemical energy in the furnace, and electric power in the cement mill. The image shows the production of pollutant emissions, which is concentrated in the clinker processing furnace. The image presents the material mixing processes that must be faced. Blending processes are essential, as they guarantee the quality of the products, and the operating conditions. The mixtures are raw materials plus correctors, fuels, and clinker plus extras. The diagram shows the production chain in a cement factory, which can be divided into 3 parts, which give rise to 3 mathematical models: raw milling, clinker oven, and cement mill. The simulation of the linear furnace must be carried out in detail, in the order of meters. This is since throughout the oven the chemical process, that converts the clinker paste into clinker is developed. For this the temperature of the oven must be controlled, which is generated by the chemical energy, produced by the materials involved in the chemical composition of the clinker paste, together with the thermal energy from the combustion of the fuels. It is used to maintain oven temperature. The chemical process is developed from the temperature of the furnace, which varies along its axis. From the chemical process, all material flows that are produced, including pollutant emissions, can be calculated. In this way, thermal energy consumption, clinker paste composition, and pollutant production are combined. Fuel blending originates from trying to minimize fuel costs while respecting emission control. The operating characteristics of the oven imply that it is a continuous process, that it cannot be stopped, that it operates under stable technical conditions, and that for long periods it works with the same chemical composition for the clinker paste. This translates into a constant production of clinker in each of the furnaces that the factory has. Each furnace may be producing a different clinker. This indicates that the furnace is not a direct part of smart grid energy optimization. The other processes, preparation of clinker paste and grinding of fine cement, can be varied, turning the machines on or off. This gives a direct possibility to participate in the non-dispatchable demand, since the scheduling of activities can take advantage of electricity price variations. However, if energy storage, such as a battery, is included in the smart grid, the dispatchable demand market, including AGC, can be accessed. The image shows the dispatch of electricity at a cement plant, including energy storage as part of the industrial infrastructure. Case: Oil Express Pipeline. Real-time optimization. Energy efficiency in the oil and gas industry. It corresponds to a project developed by hypothalamus artificial intelligence, to optimize real-time operations in an oil pipeline, based on a mathematical optimization model, which allows the pipeline to operate with 2 extreme policies: environmentally friendly, with an emphasis on energy efficiency, and economic, with an emphasis on economic profitability. The image shows the profile of the height of the terrain, through which the pipe passes. The mathematical model of the physical process of oil transportation covers the pipeline system and pumping stations. The image presents the result of a simulation, in which multiple potholes, with different types of oil, are moved along the pipeline. The matrix contains in each cell the flow of oil, and the colors indicate the pothole to which it belongs. The figure presents the comparative results for the same scenario of the two operational policies. It can be concluded. The ecological policy produces a 16.21% cost overrun, and economic policy generates an energy overconsumption of 19.43%. As can be seen, the difference is not negligible, and is due to the way in which the electricity supply is contracted, which in this case varies hourly. Epilogue. As stated by the company Inside, a specialist in industrial process optimization. A realistic mathematical model is the key to considering all the factors involved in industrial energy efficiency. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.